Let's get straight into it. Let me hop over to where I am. I gotta log in, motherfucker. Okay, that's a resistor right there. Alright, anyways, that's our capacitor. It just comes down to, you got your two plates separated by some dielectric material. In case you know, we have a specific capacitance. It's already been... the resistor is a component that it's like kind of determines the current based on the voltage across it, right? Capacitor itself, which actually we're going to indulge in right now, acts differently in, like, if we're going to do like a transient analysis compared to a frequency analysis. Right now we're about to do a frequency analysis, meaning our input is some like cosine or sine wave that has a particular amplitude and a particular frequency. It's just a very basic fundamental filter. Our high pass filter, okay, with the capacitor in series with the resistor, but then we're going to take the output at across the resistor. The resistor is the high pass component. The capacitor is the low pass component. So if we were to have the same series circuit right here, capacitor in series with a resistor, but we took the voltage across the capacitor, then we'd have a low pass filter. Meaning, like, you know, when you say low pass filter, it's just as simple as frequencies. It's going to pass a low frequency. Okay, we got a couple more resistors here. Common for the operational amplifier's feedback loop to be connected to the inverting input. This is the non-inverting input. The inverting input is negative. And so it's common for the feedback loop to go to the negative. This resistor at the end of it connects to ground. Operational amplifier, we have a capacitor here, we have a capacitor here. Label that as C2. And we have our resistors. We have available a 1.5 microfarad capacitor and a 220 picofarad capacitor. Okay, capacitor. We have a variety of resistors between 100 and 100 kilo ohms. Okay, so we can't grab nothing above 100k. We can't grab nothing lower than 100 ohms. Okay, RS equals 20k. All right, so we're gonna say RS equals 20k. These are our knowns. All right, 20 kilo ohms. Make it clear, make it obvious. Okay, I want there to be two break frequencies for this filter: 10 hertz and 20 kilohertz. I want mid-band frequencies such as signals around 1 kilohertz to be amplified by about a factor of 2. Okay, break frequencies. All right, break frequencies. 10 hertz, right, and then okay, we want attenuation for any frequencies below 10 hertz, and then attenuation for any frequencies above 20 kilohertz. Okay, right here at the beginning of the circuit, we have our high pass filter. Therefore, this operating as a high pass, this operates as a low pass because of where our reference voltage is being taken. Well, I'm going to have to look up the equation for break frequency. Op amp examples, input resistance. We want to jump back to the frequency analysis. Speaking of impedances, I want break frequency though. Break frequency. That's the Euler relation right here. It's just our alpha. 10 times 2 times. So now we're working the lower frequency. 10 times times 2 pi. E to the negative 6. Inverse of that. Okay, so that's within range. 10 hertz times 2 pi times C1 equals 10,610 ohms. We're applying the 10 hertz to the high pass filter because we want 10 hertz and up. We're applying 20 kilohertz to the low pass filter because we want below 20 kilohertz. 10 hertz and up. Okay. 10 hertz and up. 20 kilohertz and below. This is C1 equals, this is C2. So we've determined that. We know that RS is 20 kilo ohms. And now we need the value of RF. This also wants mid-band frequencies, such as signals around 1 kilohertz, to be amplified by about a factor of 2. Let's write down what we know. We know that we've been given an ideal operational amplifier. All right, so in an ideal world, our non-inverting input is approximately, we're just going to call it equal. It's approximately equal to our inverting input. Our non-inverting input is approximately equal to our inverting input. So this is because an ideal operational amplifier has a loop gain of infinity. So now I can do node analysis and I can figure out what V positive is. Actually, I don't even need node analysis for that. I can figure out what V positive is easily with a voltage divider relationship. I can figure out V negative through node analysis. A little bit of node analysis. So, okay, so we can know what's going on at the positive node with ease because it's just a voltage divider relationship. Okay, so the voltage dividing relationship is going to look like this. V positive. Again, right? Let's define this is V positive. This is V negative. Also known as our non-inverting input and our inverting input to our operational amplifier. Okay, so V positive is going to equal VI multiplied by, look at these these components in series. We're taking the output of the voltage across R1, so it's going to be R1 in the numerator, and then the sum of R1 impedance of C equals 1 over C times S. Where S equals imaginary number times omega. This is where we're at, 1 over C 1 S. Okay, so it's going to be R1 C1 S plus 1 over C1 S. That's going to go into the numerator. X. We're going to call it Vx. Alright, we're just going to give the node some sort of variable. Negative over, okay, so this is Kirchoff's current law, okay? Also known as the junction rule. Say that V negative because this is the voltage across here in reference to ground, okay? Everything's in reference to ground. So V negative over RS negative. So minus, we're going to write it as V negative minus Vx, right, divided by RF, okay, RF. Figure out exactly where I went wrong. Okay, so the voltage divider relationship would look like this. So it'd be like V out equals Vx multiplied by, we're taking the output at C2, so we're going to have C2, 1 over C2S, where S equals J omega in the numerator, divided by the sum of 1 over C2S plus R2. Going to equal, right, 1 over C2S, and then we have R2 C2S, 1 plus R2 C2S, all over, yeah, so it's going to be like this, divided by C2S. So V out equals Vx multiplied 1 over 1 plus R2 C2S. So now we have something for Vx, and we can just plug this in, and we're going to plug in V positive for V negative. So it's real easy. So we have V negative multiplied by 1 over RS. Right now they're in a complex form. We have an imaginary number. And so I want to simplify them into just their magnitudes. So I'll show you what that's like. I'm going to go ahead and do it just because, I don't know, I'm going to see where this takes me. So let's say we want the magnitude of Vx. this whole thing, but again, we want V out to the magnitude of V out. Here, let's write this down. The magnitude of V out to equal 2 times the magnitude of VI. VI. Okay, that's true. So now at a particular frequency, which we've already discovered earlier, the frequency is 1,000 hertz. And so to get our angular frequency, which is applicable to the equation, we're going to have to multiply that by 2 pi. And then that's just going to get us our dub, our omega. All right. If you have 2 VI, we have a VI on the left-hand side that's going to be divided. So we can just get rid of the VIs. So we can just put 2 here. 2, that's going to be left over. Multiplied by RS, which is 20 kilo ohms. And now this whole everything in the parentheses equates to approximately 1. It's a little greater than 1, but everything in the parentheses approximates to 1, and so now we multiply by RS, and we're just essentially RF is equivalent to RS, and that's exactly what we got. We got 20 kilo ohms. Excuse me. Complete this program I've been in, and so once I complete that, then we can start really reaching out and doing some experimentation. This is Learn Electronics, the engineering of technology, and this specific one was op amp circuits. So stay blessed, stay up, keep working hard.